So radiation is not good for biological organisms. There is acute radiation damage. This occurs from exposure to large amounts of radiation in a short time. This is the sort of thing that happens when a nuclear bomb goes off, or when you have an exposed nuclear reactor core, nuclear accident at a power plant. When you have this acute radiation damage, a large number of cells die. And the ones that die the most are the ones in your immune system and the ones in your intestinal lining. These are the ones that are rapidly dividing. And so the symptoms are a weakened immune system and an inability to absorb nutrients. So a mild case of acute radiation exposure is possible to recover from that, but in a more extreme case, death usually results not directly from the radiation, but because of infections that your body's no longer able to fight off because of the radiation damage. Radiation increases the risk of cancer. Small doses of radiation over long periods of time can cause this. Radiation can damage your DNA. Radiation ionizes atoms and molecules, and that can damage your DNA. In case you didn't know, DNA is what your cells carry in them that gives them the instructions for how to reproduce and grow. Usually, radiation would kill the affected cell, but sometimes the cell survives and just grows abnormally. It's actually better if it dies. Just give up and die instead of growing abnormally and causing cancer. Cancer is cells that are growing out of control. The cancer risk increases with increasing radiation exposure, but we cannot determine the exact threshold. We can't determine, okay, well, what is the level at which radiation exposure is safe, and where do you cross the line into increasing cancer risk? For one thing, in order to do a really good study with that, you'd need a whole bunch of human volunteers. No one's lining up for that, right? The other problem, which is one of the reasons I like chemistry as opposed to biology, is there are way too many factors, too many variables when you study humans, right? Because it's not just how old, male, female, there's diet, there's genetics, there's all these different variations, and so you just can't do very good studies. So we know that more radiation causes increased cancer risk, but it can't really be quantified, and you can't really say, okay, well, this much is safe. Radiation can cause genetic defects. So if the DNA in the eggs or the sperm are damaged, then obviously the offspring could be affected by that. Interestingly, we have observed genetic defects like this in laboratory animals, but such defects have not been verified in humans, not even in studies of survivors from Hiroshima, which, that was like, it was a horrendous tragedy, right? All those people died and were exposed to radiation. But scientists need to take advantage of things like that and use that negative event and study the outcomes to learn for the future. So they've studied the survivors from Hiroshima, cannot demonstrate any genetic defects in their offspring. So while it makes sense and we see it in animals, we haven't directly observed it in humans. I think that's kind of interesting. So how do you measure radiation exposure? This is actually a lot more complicated than you might think. So you can measure it in multiple ways. You can measure it as the number of decay events that you're exposed to. And so the unit for that is a Curie, named after Marie Curie. The abbreviation is CI. One Curie is 3.7 times 10 to the 10th decay events per second. So what's a decay event? Well, that could be, like if you're talking about a naturally radioactive isotope that's decaying by alpha emission, that would be one alpha particle being spit out. That would be one decay event. So this is a lot of decay events per second. So we can measure exposure that way. It's not an effective measure for how much biological tissue damage is occurring, because different kinds of radiation produce different effects. Is it beta emission? Is it alpha emission? Is it gamma? Those have different effects for the same number of decay events. So a better way to do it is by a radiation dose, which is the amount of energy that's actually absorbed by body tissue. So 2 units here are the gray. I know it's a color, but it's also a unit of radiation. The gray and the rad. So a gray is 1 joule per kilogram of body tissue. A rad is 0.01 joules per gram of body tissue. And rad stands for radiation absorbed dose, RAD. Measuring how much energy is absorbed still doesn't account for what kind of radiation was it, so it doesn't really tell us how much damage was done. Gamma rays have low ionization energies, alpha rays have high ionization energies, and then there's differences in penetrating power, and so it's actually quite complicated. Another way to account for this is by using a biological effectiveness factor. It's called RBE, for relative biological effectiveness. That's a correction factor that you apply to the dose in rads to get the dose in REMS, a Röntgen equivalent man. It's not complicated at all. So you take your dose in rads, radiation absorbed dose, and you multiply by this relative biological effectiveness factor to get the dose in REMS. The RBE is going to be different for different kinds of radiation. So the RBE for alpha radiation is much higher than for gamma radiation. So here's an interesting table from your textbook. This is showing radiation dose by source for persons living in the United States. So we are exposed to natural radiation. That first one, a 5-hour jet airplane ride, you might say, well, how is that natural? Well, the radiation isn't from the airplane. You're getting more radiation because you're flying high. So that's going to give you 2.5 millirems per trip. There's cosmic radiation coming in from outer space. We're getting about 27 millirems per year from that. There's terrestrial radiation, that's radiation from the Earth, 28 millirems per year. There are natural nuclides, radionuclides in your body. There is radiation in your body, radioactive nuclides. So that's going to give you about 35 millirems per year. Radon gas, on average, 200 millirems per year. That's the lung dose rather than the whole body dose. Radon gas exposure is going to depend much more strongly on where in the United States. I grew up, part of my growing up was in Iowa, and Iowa has a lot of natural radon gas. And so there, people also have basements. Basements are so useful. But basements can also accumulate a fair amount of radon gas. And so there, in addition to a smoke detector and a carbon monoxide detector, you also would have a radon detector in your basement so that you could know if you were getting radon gas. Diagnostic medical procedures are going to give you some exposure. And you can compare these numbers to things that happen naturally. So a chest x-ray, 8 millirems. Well, you're getting a whole bunch of stuff just from your environment, naturally, and that you can't avoid that at all. So obviously you don't want to have a lot of extra x-rays. We only want to do those if they're warranted, but the amount of radiation that you're getting from those is not unreasonable, right? Mammograms, barium enema, doesn't that sound fun? Upper GI test, thallium heart scan, CT scans. If you do your abdomen and pelvis, CT scan 1,000 millirems. So that's significantly higher. Then we have consumer products, building materials, luminous watches. They don't use radium in those anymore, but those do have hydrogen-3, and I can't remember the name of PM. What is PM? It's okay, it doesn't matter. PM-147. Tobacco products. Look at that one. You smoke 30 cigarettes per day, 16,000 millirems per year.
Straight to your lungs.
Yeah, straight into your lungs. So, tobacco products are bad for you in more than one way, right? Any questions about this? So it's going to take a lot more than the average amount of natural radiation or the radiation from a medical procedure. Mr. Balo is doing something fun, making whooshing sounds. It's going to take a lot more than this to produce any significant health effects. In the previous table, the doses listed were in millirems. Now these doses here are in rems. So all of these numbers are 1,000 times larger already. And so these are effects of instantaneous radiation exposure. So we begin to see some effect from 20 to 100 rems, not millirems, rems. Decreased white blood cell count, possible increase in cancer risk, we're not sure. A little higher radiation sickness, that generally includes vomiting and diarrhea, because the radiation is attacking your intestinal lining. So it makes sense that that would make you sick to your stomach. Skin lesions increase cancer risk. 500 is going to result in death. It's going to take a while. 1,000 death, shorter time, 2 weeks. 2,000 death within hours. Isn't that cheerful?